So my name is Tal Frangi. I'm from Google Tel Aviv. I'm going to give a talk about MapReduce. I've been working in Tel Aviv office for a year and a half now, done several projects from networking to ads, several different projects. So I'll talk about MapReduce. This MapReduce drives a lot of Google infrastructure, of our backend processing, and it gives you a peek to the backend, to the data center of Google. Google does not give you any direct access to MapReduce as it is, but as we'll see towards the end, there's an open platform, the open tools to do something like MapReduce that you can use. So it's not a specific API, it's more to tell you about what's happening behind the scene of Google backend. So first of all, MapReduce is not something new. The concept of MapReduce, which I'll go over, is something that existed in Lisp, in parallel Lisp for 30 years. So it's not innovative in that sense. It's innovative in the implementation and in the details we'll see. So what's the trouble we're trying to solve? Dealing with the large amounts of data is very hard. All the numbers you'll see here, the presentation here is about 3 years old. We are not changing the numbers, and I'll tell you in a minute why. So for example, suppose you want to go over the whole web and index it, or do some kind of analysis of the whole web. So first of all, how large is the whole web? So you can see the arithmetics here, 20 billion pages, about 20 Ks each page. You get 400 terabytes. That's a lot of data. Just storing it, it's about 1,000 hard drives. If you want to do something with this data, index it or do something with this data, it would take you, if a computer reads about 50 megs a second, it would take a single computer 3 months just to go over all the data. So what do? As you know what Google does, Google just uses many machines, a lot of machines. So on a stack of 1,000 machines, you get it then to less than 2.5 hours. So this is how an old data center of Google looks like. You can see racks of 40 computers, and each such rack is connected. All the computers in the same rack are connected through a switch, and all these racks are connected to a central switch, and you get thousands of computers connected together. So one of the problems, you know what's the biggest problem of building such a large data center? Heat. So the first problem is heat. We squeeze about 5 times more computers than normal data centers into the same square meter or square feet. So you got a huge problem of heat. And the second problem, as I said, is electricity. We get so many computers in a single data center that electricity becomes a problem and becomes a cost. So typical machine, again, these slides are a little old. We don't want to expose the exact numbers of computers or the exact way our data center are built, but a normal machine is 2 or maybe 4 CPUs, has several gig of RAM, and has about 6 hard disks with a lot of storage on them. So we got a pretty healthy machine, but not the top of the line. We'll see in a minute why not the most expensive or fancy machine. So when you build something to span over thousands of machines, and you want to be able to process a lot of data in parallel, the consideration you take are a little different. So it doesn't matter for you to have a single machine which is the fastest. You don't buy the fastest machine because it doesn't really matter. What matters to you is how I built a data center in a good cost that can process the whole web. So the processing power per dollar is more important than how fast is a single machine. The single machine, if it's faster or slower a little, it doesn't really matter. Because if it's a little slower, you can always add another 1,000 machine, right? So the single process or the single thread throughput doesn't really matter. The other thing that changes when thinking about this large-scale parallelism is at your home, your computer breaks once every 3 years. That's the average. If you have 10,000 computers, you have 10 of them breaking every day. So you need to think differently about how you maintain such an operation. And the last thing, buying the most expensive HP or IBM or Dell server that lasts, that is more reliable, doesn't really help. Because if you buy a cheap computer and it's MTBF, its time to last is about 10 days, 1,000 days, and you invest 2 times the money to make it 500 days, 2,000 days MTBF, you still have to deal with many computers breaking. So you have to deal with it anyway. So you're better off investing the money just buying more computers, which are cheap and give you better performance to dollar ratio. So that's something to keep in mind, and that's in a way what made Google profitable. This insight that we need to be cheap on the serving side, on the infrastructure side. We did it at the beginning. We were much cheaper than any other company. So when you come to, you have such a data center with thousands of machines breaking all the time, and you want to write a program for that. You want something to run on this. So it is not simple. You need to think how to split your program to 1,000 or 2,000 machines. You have to coordinate the software. Your software is running in pieces. They have to coordinate. You have to recover from failure. You have to, if something fails, you want to know how things progresses. You have to collect status from all these machines together. So all this work, each and every team that developed a software for 1,000 machine, 2,000 machine, had to do on its own. So for every project that writes some kind of software to run on so many machines, he had to repeat that. So in 2003, someone sat down and said, how can we take most of what people do on large clusters of machines and give them a library or an infrastructure that would be easy to program and that will handle all these for them? So this is MapReduce. MapReduce is a simple model that gives you a way that most of parallel application can be programmed, and it will handle or hide from you all the details of communication, of handling faults, of things breaking, and this is the idea. As you'll see, the interface of MapReduce is very easy. Okay, so how data flows in MapReduce? You read a lot of data from a lot of disk. You write a component that is called map. The map goes over the data, filters it, and collects the meaningful data from it, and then take it and deals it like cards to the reducers. You have thousands of mappers running over the data and dealing it to the reducers. Each reducers get his own pack of data, and the reducers do the aggregation or summing of data. If you think of it, if you look at many queries you write in database, you have select this and this from where, and then you have group by having. So if you're from database field, you can think of the map as the part that selects the records, and the reduce stage is the stage that does grouping and summing. But it's in a very large scale. So what do you need to write is 2 functions generally. You need to write something that takes the data and creates records of interesting data, and something that takes the interesting data from the mapper and sums it up. The best way to understand it is just to take an example. So suppose I want to build a histogram of words for all the web, meaning how many times did the word "the" appeared? How many times did the word "pumpkin" appeared? You want to just build a huge histogram of all the words on the web. So you need to write two functions. One that goes over all the web pages and finds the words, and one that sums up for each word how many instances you saw. So the map gets as an input, each mapper gets as an input a web page, the name of the page, and a huge data that contains the page. And what does it do? It just goes over the page, splits it to words, and for each word it sees, just say, hey, this word, 1. This word, 1. This word, 1. So it's a code you can imagine yourself writing, parsing the web page, splitting it into words, and just saying, hey, this word you can add a 1 to it. What do you do on the reduce side? You just for each key, for each word, the word is the key, you just sum up the results and you write it down. So it's a very simple example. It shows you many of the typical things you want to do on large scales of data. So in this example, you can see if the document contained these words, I would say to 1, B1, or 1, not 1, to another one, and the reducer, this data will be split between the reducers. One reducer will get the key B and will sum up all the counters from every mapper. We have many mappers running. Each one of them that saw the word B would send it to the reducer that sums up the counts for B. The same is for each another word. But we don't have a mapper for each, a reducer for each word. We have buckets, meaning that each mapper sends some of the words to this reducer, some of the words to this reducer, and each reducer sums up for this specific word. Is the example understandable? Yeah.
Then you have several levels of reducers?
Okay, no, we don't have several levels of reducers. MapReduce is very simple, and it has only 2 stages: map and reduce, write the output. As we will see, many of the backend processes in Google are made up of dozens of MapReduces. Okay, there are certain works on different graphs of such communication, but the thing that makes MapReduce very powerful is that it's simple. Okay, it's easy to understand and it's easy to optimize. Okay, did that answer your question? No. Okay. Example of things, I'll show another example of MapReduce. Example of things that are done inside Google with MapReduce. For example, when we look at the huge source base for Google, we want to do a regular expression find on all the source code we have internally in Google. So we have a tool for that does MapReduce and goes and search for things. It does distributed source. If you saw Google Trends, that is developed in Tel Aviv, for each word, seeing the graph of how it looked, that goes over the logs, the query logs of Google, does a huge MapReduce, and for each word builds the graph for that. So many of the application and things you see in the front end of Google, indexing, everything in the back end, essentially it's MapReduce. So another example, suppose that you want for each page to know which pages point at it. So you don't want to know, it's easy to know you have a web page, where is it pointing to? We want an inverse index. We want for a specific page, who is pointing to it? Why do we want that? Page rank. We want to know how to rank this page. So that's a MapReduce. You go over all the documents of the web, and for each outgoing link, you use the MapReduce. The key is the outgoing link, and you build a list of who is pointing at it. And you build at the reducer, you aggregate for each page who is pointing to it. OK, so MapReduce is a very simple model, and it has its limitation. So the limitation is you cannot join. So again, I'm going back to the metaphor, the SQL metaphor. So you can do select that and that from, where, group by, having, etc. But you cannot join. Because join, if any one of you are working with database, join is the one thing that is the most difficult part of SQL optimization, right? And when you have large data sets, that's become even harder. So MapReduce does not join. It works on a single flow of data and takes the data and sums it. But we do need to join in several cases. So here's a simple example, an example where, for example, I want to go over all the web pages and find up for the the predominant cities in the world, which pages relate to New York, to London, etc. So I go over all the pages, and I want to see which one of them relates to this city. So instead, how do I do this join between all the pages, the web pages in the world, and the list of cities? So the way I do it is I join by copying the lists. Because I have a join of a huge data set with a small data set of the cities of the world, I can send to each mapper, to each of the computers that are running, the small data set, the data set of the cities of the world. And this is an example of how you can do sometimes joins, even with MapReduce, with tricks. So in a normal database, this join would be optimized to do exactly that. But when you work with MapReduce, you as a programmer need to do that by hand. You need to remember to send to each mapper the list of cities. So again, each model has its limitation. MapReduce is very strong in going over a large set of data, but has its limitations. Just going back to the data center for a minute, when I said stuff breaks, actually the data center are built in a way that when a machine breaks, it is not replaced immediately. They have a weekly or a daily walk around where they take the broken computers, put new computer, and the computer just boots up and installs the new image. When a hard disk breaks, the hard disks are connected with Valcore, Scotchim, and they just take it off, put a new one. So it's very, very easy to maintain such a data center. OK. The MapReduce code came out, the library was released to Google internally at 2003. And as you can see, this is the number of internal programs using MapReduce. As you can see, many, many programs moved and started to use MapReduce. MapReduce today, if you start working at Google, probably the first project or exercise you'll get to do is writing some kind of MapReduce, doing something on 2,000 machines or something like that. So how does it look from the hardware perspective? So we have the data split among a lot of disks. We have machines that contain the data running the mapper, for example, going over the data and splitting it into words. Each mapper then builds what I call a bucket. You take all the words that belong to a specific shuffle and put on your disk. So if I have 2,000 mappers and 10 reducers, each mapper puts the data into 10 different buckets. Some of the keys to here, some of the keys to here, some of the keys to here. This is the map stage. After that, there's the shuffle stage, like shuffling cards. Each reducer gets his own pack to it. And then there's the reduce stage, where each reducer goes over the part of it and sums it up. What? Not to each other, only to all the each shuffler talk to all the mappers. Each mapper talk to all, so it's m by n. So it's.
So the mappers put the data in the correct shuffler.
Actually, they put it in some kind of temporary file, and the reducers go and read from all the mapper. They take the data from them using RPC. No, the data is divided into a lot of pieces. If I have the web, I have it on thousands of disks, right? And each mapper runs on the disk he owns, and all of them together go over all the data. Okay. Okay. So typical numbers is you have 2,000 machine, and you have 200,000 mapper jobs. And each of them go over their pieces, and the work is divided into 200,000 pieces. I won't go over it all, but there's a single master. I haven't shown that yet. There's a single master that handles everything. For example, the master pings each and every mapper. He gives it the data it needs to go over. The mapper goes over it, and it tells it it's done. During the time it goes over the data, the master pings the mapper all the time to see what? If they are still alive. A machine can break, things can break. So if a machine can break, the master takes the same data he gave this mapper and assigns it to a different mapper. So the recovery is in the level of a shard, what we call a shard, which is a piece of the data. The data is split into few 60 megabytes, 64 megabytes shard pieces, and each piece is assigned to a mapper. And if this mapper dies in the middle, we give it to a different mapper. Okay, how does it look? How does it look from execution perspective? So suppose we have 4 machines here. This machine started to work on the first piece of data, and it finished. The master immediately gives it another piece of data. And as we can see, either because this machine is slightly faster or because it got easy to process data, it finished the two first shard before the second machine even got finished with a single piece of data. After the mapper finished processing the first stage, the reducer can start reading the data from the mapper to it. As you can see, both reducer, each of them read the data of the first map. As we say, each mapper deals the cards to all reducers. Only after all the data has been read by all reducer, the reduce stage, the summing up, can begin. So this is how the console. We have a console where we go and look look over the progress of the MapReduce. So this is a MapReduce. You can see how many megabytes. As you can see, this is a MapReduce of about 1 terabyte, and you can see the axis below. You can see there are 500 machines running, and this is the map stage. The green is the map stage in percent, and the red is the reading stage, passing the data from the mappers to the reducers. And here is the reduce stage. Each pixel here is a machine doing its work. As you can see, the data progresses and the input and output numbers progress. As you can see, we are near the end, and there are still, you can see, 2 active reducers. And they keep us, we are still waiting for them to finish to know that everything is finished. Now we have 1, and we are still waiting for him. We'll talk about it at the end. What we do with everybody is that we still have 1 left at the end. So this is how the console looks like. So fault tolerance, I've mentioned that. The master sees a failure, and it just gives a different shard, different piece of the data to a different mapper or a reducer. Okay, so the master, if the master fails, we restart. The master does what we call a checkpoint. It writes its status once in a while. Status means what was done, what was not done. It writes its status to the file system, which is backed up for once in a while. And if it failed, we need to restart the whole MapReduce from the point it failed. So we can just do a restart. OK. So several refinement, and in fact, these refinements are what makes things much faster. So for example, in many cases, you can do part of the reduce on the mapper. For example, in the word count, if you have a lot of the words "de" inside many documents, you don't need to send the 1, 1, 1 to the reducer. You can sum part of the data locally on the mapper and just send the sum to the reducer. So if some of the data can reduce locally in the mapper, you can do that. So that's one refinement. Backup task. As we saw in many cases, at the end, we have 1 or 2 reducers holding us down. This may happen because the hardware is screwed up. So the worst thing that can happen is not that a machine is dead, but that it's barely working. It's working, but very, very slowly. So when you have the last task working and we're waiting for them, you can say, OK, they're working, but let's consider them dead and give their work to another task. So that's another refinement. We'll see the influence of this immediately. Local optimization. Google, the files or the data Google uses is based on Google file system. You can read about Google file system in articles. So Google file system splits the data between many disks and keeps multiple copies of each part of the data. So one thing that MapReduce does is if you have the data stored here in this GFS server, run the mapper on it, and not on another machine try to communicate through the network. If you run it locally on the same place where the hard disk is, you get much faster execution. I'll skip that. OK. So performance. MapReduce, there's a very well-known test called TerraSort, which is sorting 1 terabyte of data and sorting it over a large number of machines. This number is from 2003. It's 14 minutes. Today, I'll show Hadoop. If you'll look at public domain MapReduce, which exists, public domain MapReduce does TerraSort, sorting of 1 terabyte of data in about 2 minutes on 900 machine. The machine got stronger, the technology got stronger, but it still is amazing. I already talked about what it did to the Google code, to the indexer, to all infrastructure. So I want to show you something about how things are working in terms of timeline. So when you have almost 2,000 machines and you do a TerraSort, you try to sort 1 terabyte of data. So normally, if you just run it on a 1800 machine, you get it running in 800 and something seconds. If you kill 200 machines, they just die in the middle, you see very little influence. You see instead of 839, you get 886. If you remove the feature of waiting for the backup task, you see it's very, very long. Those two last tasks that keeps us from finishing actually takes us a long time to do that. So the backup task is a very important refinement to the model. That's it. Things that you can read about it. In Google Labs, just go to Google Labs and search for papers. There are a lot of tens of papers written by Googlers. MapReduce is one of them. You can see all the data in this lecture there. There's papers about GFS and how it works. So if you want, for me at least, before I came to work for Google, I just read the papers. And actually, when I started working the papers, I discovered I know about GFS, MapReduce, more than people inside Google because they just didn't read the public article. So just go and read about it. Hadoop. We try to do Google has an initiative to teach MapReduce in university all over the world. So we're trying to do that in Tel Aviv University maybe this year. It was done in MIT, in University of Washington. And we cannot give you the code for MapReduce. It's not public domain. But there's a public MapReduce called Hadoop. It's part of a Apache group project called Notch, which is a public domain search engine. So if one of you is thinking about building a search engine, first look at the open source solution. It is all in Java. And actually, the Hadoop won the 2008 TerraSort contest. So it actually works very well. Our MapReduce didn't participate this year. So go and check it out and see. If I was a startup today and I needed to process very large amounts of data, I would certainly look into the open source solution. That's it. Questions? So, no. So the granularity of handling the data is the shard, is the 64 megabyte. So it does not know the exact byte in which the error occurred. It just knows that in this piece of data, I divided the data to pieces that are 64 megabyte long. In this piece of data, I failed. So with tables, you're talking about the table it needs to hold in memory or whatever, are much smaller than what you think. That's it does not fetch anything. The data does not pass through it. It just tells him, hey, you go and process this piece of data. Regarding your first question, so MapReduce as a concept did started as a functional concept in Lisp and in other languages. But the actual implementation is not relevant. We have, I can write internally, I can write MapReduce in Python, in Java, in C++, whatever I want. And specifically, the public domain version is Java. So I imagine you can, if you want to have it in a functional language, you can do that. It does not matter. Okay. Other questions? Yeah. What? Okay, debugging is a very, it's a very hard question. The first thing is you can run MapReduce locally on your machine. So first of all, you take a small amount of data and you run it, there's a debug mode where you run the MapReduce on your machine. So that's the first thing to start. But when you have something failing over a large amount of computers, it's a problem. So there is where logging is very important. So we have mechanisms for the mappers to log, and someone collects all the logs and we can look at them. So it's part of the problem of running such a large system. It's right. Okay. So first of all, MapReduce as I told you, the software itself, there's a public domain version, not written by us. By the way, it's supported by Yahoo and by IBM. So you can take Hadoop and use it. If you want to use our infrastructure, the infrastructure. Okay. So the first, I'm stealing John McAllister's talk coming next on App Engine. The first question we had about App Engine is what if I want to do a backend task? Not only a front-end task. I get an HTTP request I want to return. I want to do some report. I want to do something in the backend. So I'll let him answer that. But it's a pain for our developers when we don't have yet the answer. Okay.
Yeah. What would you recommend for applications that need join, lots of joins?
Okay. So first of all, I don't know how many. The Oracle has a a database running on 100 machine cluster called, I don't know, Real Application Server 1, or it's Oracle 10 as a solution for such a big application. It's limited to 100 computer, which for Google is small. But for many applications, it's good. MySQL as a solution for 48 computer database, for a cluster of 48 computer database, and they do amazing things there. So you can actually use a database. So it depends on how large is your problem. Our scale are very rare. I mean, doing the whole internet is not something you do every day, okay? Other questions? Yeah.
Is the MapReduce only used for back-end processing, or do you see maybe in the future where it's faster, any like real-time uses of MapReduce?
Well, I don't see any real-time user. I mean, it is optimized for getting you the largest amount of data in the smallest cost. It has no real-time optimization. Yeah.
Can you say a few words about big table?
It would be, by the way, in the papers, go to Google Labs, you can learn about big table from there. There's a paper, a very good paper on big table. We expose a lot, so you can read about it. Yeah.
What about locality data?
What?
An application like a crawler needs to have some locality of the data.
What?
You want to process similar records, similar URLs on the same location. So
Locality is in pages from the same site.
yes, for example, on some key, for instance.
Okay. So the question is sometimes when you want to optimize is, what do I get in the same shard? So in the same piece of data, I want to allow the mapper to do most of the work with data that is similar that will save us a lot of reducing. So in many cases, when you want to get data that belongs together, you do a first stage of MapReduce that somehow arranges the data for you to be close together, and then you do the MapReduce that does the actual arrangement. So as I said, in many cases, there are 10, 20, or 100 stages of MapReduce in a very large pipeline of processing.
So a crawler can be implemented as a series of MapReduce.
No, crawler is a different thing. Crawler is something that does a lot of HTTP requests. It's not a backend. It's something that does a
But to do crawler, for example, it has to write to the same database.
no, not a database, to the files, right?
File system.
So the crawler takes the data and writes it to the file system. Then someone else starts processing it, and that processing takes several stages of
My
MapReduce.
question is regarding an application like the crawler. How do you make it run locally?
So the question is, what is it optimized for? I mean, if you want to optimize the crawler, for the point that the processing would be easier, I'm not sure that's the best thing to do. You want to optimize the crawler for a lot of things, for how does it access the web, how fast does it save the data. So I'm not sure that's but again, there's a full-scale search engine called Notch with Java source code. So it's a good place to start to look at the ideas, how it is implemented. Other questions? Thank you very much.